All right, so in this lecture, I would like to explain an article from 1995, The Geometry of Graphs and Some of Algorithmic Applications by Nathan Lineal and Aaron London. This is a very important article. Yuri Rabinovich. So many other articles are maybe inspired by this article, especially the works of Itai Abraham. So what's that? This is inspired by the work of Bourgain. So in this article, they provide a proof of Bourgain's in a very interesting way. So that it could be useful for further algorithms. So in random polynomial time, Bourgain says that any metric space may be embedded in LP of order log 2n with distortion, as you know, as I've said several times, O log n. So this is the distortion. So the proof is very interesting and very inspiring for generating new algorithm. So we randomly pick order of log n sets of such as A from vertices of your graph, but with cardinality less than n, and we map, as we have done several times, to the distance to the set. So before proving that, I need to write some definitions. As you know, this is the ball that the distances are less than rho. This is a closed ball because of this. And this is an open ball as well. So if you're familiar with topology, this is the open ball. The xy is less than rho, but not equal to. So rho of t is least radius rho for which both of them. Remember that bx and rho. So the cardinality of this is greater than 2 to the t, and so both of them should be satisfied. And b of y with rho, so it holds for point y as well. So what we are doing is that we are creating some rho t's such that as long as it is less than 1 to the 1/4 of the xy, we can define this. So the geometric idea is that you have a point y, and so this is rho t minus 1, and so next step is rho t, and the intersection of this with this a, this is a, the intersection is just this area. And we have also another point x, and again we defined rho t minus 1, and also rho t like this. And the distance between point x and a, this is the distance between point x and a. So we can say that we have defined rho as long as this holds. So we define as long as that, and t hat is the largest index, such that rho t plus 1 is equal to the x and y divided by 4. And the observation one is that b of y and rho j and b of x and rho j are always disjoint. So they are disjoint. So these balls are disjoint. And let me write this. So the important things that the point I want to make is just noting that d of y and a is less than rho t minus 1. And d of x and a is greater than rho t. And combining them, we can easily see that d of y and a minus d of x and a, the absolute value is greater than rho t minus 1. And this is interesting because we can do lots of things like, for example, telescopic sums. So it has useful properties. So you see that here until here it is dxy divided by 2. And here this is the distance between x and y. And so you see why we have defined these ratios like this in order to make sure that they are disjoint. So the proof is like this. Therefore, for almost every choice of A1 through AQ, you can write this sum. Why? Because you are trying to write the LP norm. So it is the sum of the coordinates for L1 norm, and so P could be anything. But let's say P is just 1, and it's just L1 norm, and then the sum of all these coordinates, we can write it like this. And as I've shown you, this is greater than log n rho t minus 1 divided by 10. And since we randomly select this Q, which is of order of log of n sets of cardinality 2 to the L, we can write this as I from 1 to capital Q, d of x and ai minus d of y and ai. This is greater than log n 10, and we are now close to the telescopic sum, which is I is from 1 to t hat plus 1, rho I minus 1. And since we love telescopic sums, because it reduces to some interesting and easy things, so this is just rho t plus 1, t hat plus 1, and this is greater than, I've shown you geometrically that it is easy to see that this is greater than d of x and y. So we use the triangular inequality here, that d of y and a is less than d of y and x plus d of x and a. And then we can use d and x and y, right, for this. D x and y is greater than d of x and a minus d of y and a for any set A. And because for any set A you can write this, then you can write the sum of d of x and ai minus d of y and ai is less than c log 2 and d of x and y. And so our map is just x goes to the x and ai, just scale it by q to the 1 to the row, from I from 1 to q. So for every I, we can define this tau x and y as it is defined in the article. This is from 1 to q, d of x and ai minus d of y and ai to the p, to the q, and all of them to the p. Remember the LP norm. And so if we define tau like this, then it is easy to see that tau of xy is less than d of x and y. And on the other hand, d of x and y is less than 40 I from 1 to q, and d of x and ai minus d of y and ai log n is order of log n q, sum of I from 1 to q, d of x and ai minus d of y and ai. And by monotonicity of the pth moment average, it is less than order of log n tau x and y. So we have proved that. We have proved this interesting and important theorem, that in polynomial time, for any metric space x and d, it can be embedded to LP of order log 2 n with distortion or log n. And this is the paper from 1995 by people like Yuri Rabinovich. So this is another proof of Bourgain theorem. And why I'm talking about this article from 1995, because many articles after this are inspired from this theorem, even this proof. Even the proof is very interesting. So thanks to the guy Yuri Rabinovich, Nathan Lino, and Aaron London for this interesting proof that we can create new algorithm just by inspiration from such a proof. And of course, the theorem of Bourgain is still inspiring, because every day you have a new embedding, metric embedding, just based on this idea of distance between x and a set A. A could be anything. For example, A could be in the pattern decomposition. It can be the P of x excluding P of x. So the distance between x and x excluding P of x. So now A is just this one. And P of x is a hierarchical partition that I will explain in the next 2 lectures. And in the next lecture, I would like to talk about article from 1996 from Yer Bartal. You know Yer Bartal, Itai Abraham. And so these guys are pioneers of metric embedding, modern metric embedding. So many of the algorithm, their students, I think, is Arnold. And many of the algorithms, such as shortest path decomposition, is the joint work of them. But the idea is very simple. All of them are inspired from the work of Bourgain. And so in machine learning, all of the inspiration for metric embedding is still from Johnson-Linder-Strauss, but you can develop it more and generalize it more and use Bourgain as well, Bourgain theorem as well. So in your definition of your metric embeddings, when you want to design that, you can use that the idea of Johnson-Linder-Strauss, as well as Bourgain, as well as Kuratowski embedding that I've explained before, which embeds it into a Banach space. So let us start by the article of 1996, probabilistic approximation. So the article is probabilistic approximation of metric spaces. So this is the work of Bartol. Very important article. And so the definition one is that a metric space N over V dominates a metric space M over V if for every U and V in V, the distance between U and V is greater than distance between U and V in the M norm, in the M space. So this is one definition. Definition 2 says that a metric space alpha approximates a metric space M if the distance between U and V is bounded by alpha times the distance between U and V. So the idea is that you approximate it. The alpha approximation, we approximate it by a tree. And because trees are simple, hierarchical trees are simple, then you can approximate trees with each other as well. So for trees, you approximate with beta. And so you have approximate your graph by a tree, by alpha. So alpha times beta, you approximate it by alpha times beta. Now, the definition 3 is that a set of metric spaces S over V alpha probabilistically approximates a metric space M over V if every metric space in S dominates M and there exists a probability distribution over metric spaces N in S, such that for any U and V in V, the expected distance between U and V is bounded by D of M of U and V. Remember the performance guarantee in theoretical computer science, the performance guarantee. You can check your Wikipedia if you don't remember. You have the optimal solutions, so most of the time this is NP hard. That's why we have the motivation to approximate it by performance ratio rho times optimal solution. So it is a relative performance guarantee, and the theorem 4 of this paper says that let S be a set of metric spaces over V that alpha probabilistically approximate M. If there exists a randomized algorithm for metric space in S with performance ratio beta for this optimization problem P, I mean the cost is just the distance between the vertices. So then there exists a randomized algorithm for M with performance ratio alpha beta, as I mentioned, for the problem P. And moreover, if the distribution on S is efficiently computable, then so is the algorithm for M. And the proof is very simple, as you are reading it in the paper, but it is. I write it in just one line. A of sigma is less than the expectation of a n of sigma. We randomly for a randomly metric space n in S, we choose it. And then this is because we have approximated by beta expectation of Bn of sigma. But remember that this itself is approximated by beta, by alpha. So this times becomes less than alpha beta of B of sigma. And the proof is now complete. Definition 5 that I want to explain is that a tree metric over V is a metric space corresponding to a weighted tree spanning V. Also, there is a theorem theorem 6 of this article by Rabinovich.